sense.
All right, so
Sorry.
all right, so what we want to look at here is kind of an application of calculus and derivatives that builds on something we looked at last year when we were dealing with composition of functions. When we looked at function composition, we also looked at decomposition, trying to identify the functions that were inside other functions, okay? And that's exactly what we have to do here as we look at what's called the chain rule, okay? In calculus, the chain rule allows us to differentiate things like y equals 3x squared minus 5 to the sixth, okay? How would we do this, at least up to this point?
With not factor, but like multiply out until you don't have like to the sixth.
Yeah, we'd have to multiply this whole thing out. We'd have to do the binomial expansion. In this case, we could do the binomial expansion, get just a polynomial that's completely simplified, and then we could use the rules that we've already learned, okay? But for one, it's really tedious, and for another thing, we actually have a better way, okay? And that is using the chain rule. The first thing, though, that I want to do here before we get into the rule itself is practice kind of decomposing various functions to identify what I like to call the inner function and the outer function, okay? And the one nice way that you can think of to identify inner and outer is kind of think in terms of PEMDAS. What would I simplify first? Okay, and then what would kind of be the last thing I would do? That last thing is often like your outer function. Okay, so for example here, we're going to use the notation u to represent that inner function, and we're going to use g of u to represent the outer function. Okay, so in this case here, we have, if you think about the outer function, the last thing that you would do to simplify this y equals 3x squared minus 5 to the sixth is raise it to the sixth power. Okay? So we could think of it as something to the sixth power. Okay? Now, what is that something that we're raising to the sixth power? That's our inner function. That's u, which, let me stick with my colors. That would be u to the sixth. This would be the 3x squared minus 5. Okay? Does that make sense? Alright, so now we have this one. The inner function on y equals the square root of x squared plus 3x plus 5 would be what? What's the inner function? Yeah, x squared plus 3x plus 5. And the outer function, yeah, it's the square root, okay? Now, if I'm going to take the derivative of this eventually, how would I want to rewrite this?
U to the 1/2.
Very good, u to the 1/2. And that's a good habit to get into as you're working through these. Okay? So we have that. Let's think about this one in blue here. All right, so what is u in this case?
2x plus 5.
2x plus 5. And g of u?
U cubed.
U cubed. All right. Get our purple color out here. All right, how about this one in purple? The square root of 2x cubed plus 3x. What's our u?
2x cubed plus 3x.
Yeah. And our g of u?
U to the 1/2.
U to the 1/2, square root of u. Good. Okay. And then we have this one in green. Okay. 3x squared plus 5x plus 1 to the third power. So what's u?
3x squared plus 5x.
And g of u? U cubed. Okay. So listen, the whole reason why we're doing this is to then be able to use the chain rule, okay? Now, these are two things that you're going to have to identify over and over and over and over again. We're actually going to use the chain rule as much as any other rule that we use. Later on, we're going to use the product rule and we're going to use the quotient rule. Both of those, you will use the chain rule at times within those other rules, okay? So this is a really critical rule to understand and really get down, okay? Now, let's try just a couple more. Some of these are a little bit different, but I want you to take a minute here and try these on your own, and then we'll go over them, okay? So again, identify that u and identify the g of u, okay? They're using f of x to represent that u. I don't like using g of x to represent the g of u because then we get confused because we have too many x's in there. So use u and g of u. Okay, so like I said, we want to make our g of u something that we can actually take the derivative of. Let me just show an example where someone may not do that quite right. And what they're doing is not technically wrong, it's just not going to be helpful. Like for example, on this first one, if I made u 3x, okay, I could write g of u as u plus 10 cubed. But to take the derivative of that with the rules we have now, I would have to FOIL that out. Okay, so that wasn't helpful for us in this case. Instead, what did you probably make u to be out?
X plus 10.
Yeah, make it the 3x plus 10, and then g of u is
U cubed.
u cubed. Okay, does it make sense? All right, so how about part B here? What's our u?
2x plus 4.
Good. And g of u?
U -1.
Okay, good. 1 over u, which in order to take the derivative of it, we're going to write it with that negative exponent, u to the negative 1. Okay? How about C? What's u?
X squared minus 3x.
Good. And g of u?
U to the 1 half.
U to the 1/2. Good, you're catching on. All right, how about D?
3x minus x squared.
Okay, 3x minus x squared. So then what would g of u be?
10 u to the -3.
Okay, good. We have 10 over u cubed, which is 10 u to the -3. And this is where I said, generally speaking, that outer function is the last thing you would do. Technically, the last thing we're going to do is 10 divided by whatever, okay? But you could think of 10 as almost a coefficient. It's like on part B when we had the 1. If I had a 10 above it, that really isn't going to make much of a difference because remember on our derivatives, if it's a constant multiple, you can just take the derivative and then multiply it by the constant. All right, so that is the best way to handle this one here. Yes?
Why wouldn't it be suitable to do 10 over 3x plus minus x squared for u, and then just make g of u to the -3?
Okay, that's a good question. If we made this 10 over 3x minus x squared, and then that's u, and then made it g of u into a u cubed, if you do that, that's going to cube the 10 as well
Okay.
when you plug it in. All right. Now, I guess theoretically you could do this, the cube root of 10 over 3x minus x squared, but then you're not going to be able to do that. Basically, you want to break it into parts where you can take the derivative of both parts without having to do anything else to them. Okay, that's like the ideal. I can take the derivative of 3x minus x squared, and I can take the derivative of 10u to the -3rd just using the rules I have already. Okay, that's kind of the ideal situation we're looking for there. Okay, But great question though. Now, let's actually look at the rule itself. How are we going to handle this? And here is the chain rule. I've given you right here the notation that is in the IB formula booklet. Okay? The chain rule says that if we have y equals a composite function, g of f of x, or you could say g of u, all right? What we're going to do then, dy dx is g prime of f of x times f prime of x. Or another way of saying that is it's dy dx equals dy du times du dx. All right? Now, an important detail to recognize here, this is the most commonly messed up thing, is when you are taking the derivative of that outer function, g of u, okay, you are taking it with respect to the inner function. And remember, when you're taking a derivative with respect to something, that something stays the same. Like when we do du dx, the x's stay x's. All right? Here, we're taking the derivative of y with respect to u. Okay? Now, I want to run through a number of these, kind of writing everything out for us so that we can see it real clearly. And then I want to kind of move towards where we want to end up, where we're doing more of this in our head. Okay, because as you're going to see, there's going to be quite a bit of writing, but that's okay. It's better to write more and get it right than to try to skimp off on the writing and then mess it up. Okay, so as we saw already, we could identify u as 3x squared minus 5, and our g of u was u to the 6th. Okay? Now, if I take, by the way, remember that g of u is the same thing as y, all right? So I have up here, if I take the derivative of this, I'm taking the derivative of u with respect to x, okay? What is the derivative of u with respect to x in this case? 6x, okay? 6x. And then I want to take the derivative of y with respect to u, okay? So notice here I rewrote y in terms of u so I can take the derivative with respect to u. So what's the derivative of this with respect to u? Yeah, this is just our x to the n rule. It's 6u to the 5th. Okay? 6u to the 5th. Now, here's where the chain rule comes into play. To find dy dx, I'm going to take dy du and multiply it by du dx. Notice here, if I think of this like multiplying fractions, the du's are going to cancel each other out. And I'll be left with just dy dx. Okay? Now, let's see what this looks like. We would have 6u to the 5th, that's our dy du, times du dx, that's 6x. Alright? Which we could then rewrite as 36x times u to the 5th. Alright? Now, there's one problem with this, and that is our problem originally only had x's in it, and we're asked to find dy dx, so we shouldn't have u's in our final answer. So what shall we do?
Plug in the value for u.
Yeah, we know u is 3x squared minus 5. So I'm simply going to make this 36x times 3x squared minus 5. And that will be to the 5th power. Okay? So you see, we're kind of subbing out that so that we just have a u. It's a little easier to manage while we're taking the derivative. then at the end we're gonna substitute it back in. Okay? Eventually we won't physically do that substitution those 2 times, we'll just kind of keep that in our heads. But for right now, just to see it a few times, we'll write it out this way. Okay? Any questions on that one? All right, let's work through this one. All right. We said that for this one, g of u would be u to the 1/2 power. And we said u was that inside x squared plus 3x plus 5. All right, we already went through all of that. So now I need to figure these out. Okay, du dx is what?
2x plus 3.
Very good, 2x plus 3. The derivative of x squared is 2x, the derivative of 3x is 3, the derivative of 5 is 0. Okay? All right, so now we have dy du. What's the derivative of u to the 1/2? What? 1/2
Wait, oh, u to the negative half.
u to the negative 1/2, yeah. Which we could rewrite, right? We could rewrite this as 1 over 2 square root of u. Okay, once you've taken the derivative, we don't want to leave negative exponents, okay? So now what we're going to do, again, dy dx is going to be dy du, so 1 over 2 root u times du dx. So that is 2x plus 3. And all we have to do now is substitute u back into this. Okay? I'm going to write it as one big fraction, 2x plus 3 over 2 times the square root of x squared plus 3x plus 5. Oops. Okay? So that's what that would look like.
That's all we need.
That's all you got to do with that.
Okay.
Mhm.
We don't need to put the radical.
No, we don't need to rationalize the denominators. With calculus, they're going to get complicated enough, so a lot of times we'll just leave the radicals where they are. So. A lot of the time we're not even really working with the function so much as we are plugging values in, because now, remember, we could plug in any number we want into this function to figure out what the slope is at a different point. Okay? All right, let's think through another one here. Okay? Again, we said we already identified u as 2x plus 5. This is g of u, which we could write as u cubed, right? So what's du dx?
3u to 3u squared.
That's dy du.
Oh, my bad, yes.
That's all right. That's 3u squared.
It would be 2u.
Du dx is
Just 2.
Right.
it's a line, right? U is a line, so the derivative is slope at any point, and the slope at every point of a line is just the slope too. Okay. All right, so dy dx is going to be 3u squared times 2. So that's 6u squared, and if I plug u back in, I have 6 times 2x plus 5 quantity squared. Okay. coming together in your head a little bit? Okay? So let's try these last two without writing everything out. Okay? One thing I will do on this one is I will, just so I can see it better, I'm going to write this as 2x cubed plus 3x to the 1/2. Okay? Now the outer function was what in this case?
U to 1/2.
U to the 1/2. Okay, so if I want dy dx, I need to take the derivative of that outer function. So if I have something to the 1/2, what's the derivative of that?
1/2 u to the negative 1.
Yeah, it's 1/2 u to the negative 1/2. Now instead of subbing in and out u's, I'm going to leave u there. The u is 2x cubed plus 3x. So it's 1/2 times that to the negative 1/2 power. That's my dy du. Okay? Again, notice here, the inside is still identical to what it was when we started. Okay? Because I'm just taking the derivative of that something to the 1/2 power. It's 1/2 times something to the negative 1/2 power. Okay? But now, here's where the du dx comes in. Now I need to multiply that by the derivative of the inside. Okay? So what is the derivative of this inner function?
6x squared plus 3.
Very good. 6x squared plus 3. Okay? Derivative of 2x cubed is 6x squared. The derivative of 3x is just 3. Okay? So this right here is something that's going to be helpful to remember. It's the derivative of the outer function times the derivative of the inner function. And when you're getting the derivative of the outer, the inner function stays the same. Okay? So derivative of the outer function, inside stays the same, because we're going to take the derivative of the inside and multiply it at the end. Okay? Now, this we would simplify. Again, don't leave negative exponents. Alright, I don't care if you change it to a radical or leave it as a fractional exponent, but don't leave negatives. So that 6x squared plus 3 is on our numerator, and that's going to be over 2 radical 2x cubed plus 3x. And that's our derivative. Okay. All right, one last one here. The outer function is what?
U cubed.
Something cubed, right? So what's the derivative of something cubed?
3 squared.
Yeah, it's 3 something squared. Alright, so the something stays the same. It's a 3x squared plus 5x plus 1. Okay? Now what do I need to do?
Find the derivative of the inside.
Find the derivative of the inside. Okay, so it's going to be times,
6x plus 5.
great, 6x plus 5. Okay? We can do a little bit of simplifying here. Since that 6x plus 5 is just to the first power, I'm going to go ahead and distribute the 3 to it. Okay? So that's going to be 18x plus 15. And then that's going to be times 3x squared plus 5x plus 1, quantity squared. Okay? And that'll be our final answer. So essentially, like as far as simplifying goes, if it's just a matter of distributing, go ahead and distribute it in. But don't feel like you need to FOIL, okay? We will see as we work with the product rule and quotient rule, a lot of times it's actually more beneficial to us to leave it in its factored form. but then there will be other times where we'll want to FOIL it out. Okay, so we'll kind of get a sense of when to do which when those things happen. Alright, so there's a couple others here that you can practice with. When we come back from the break, we're going to spend a day just doing these. Just straightforward ones, just practice, because really, I want you to get so comfortable with the mechanics of this that you can just write these down. You know, for example, you may rewrite this one as 2x minus 1 to the negative 2, but I want you to get to the point where you can say, okay, that's 2, or negative 2 times 2x minus 1, now that's to the negative 3 times the derivative of the inside is that, so it's negative 4 over 2x minus 1 cubed. Alright? I want you to get that comfortable with these. Alright? Even with something like, say, d. Alright? We have x cubed minus x squared to the 1/3 power. So, the derivative of that with respect to x is going to be 1/3 times that something to the negative 2/3. Okay, and the something stays the same, but then I have to multiply that by the 3x squared minus 2x, the derivative of the inside. Okay, and now I'm simplifying it. Alright, 3x squared minus 2x over, and you can leave this as a fractional exponent, x cubed minus x squared to the 2/3. Or if you want, you can make it the cube root of that squared, if you want to translate the 2/3 power there. Okay? But I want you to get that comfortable with these, so that's why we're going to do a lot of practice when we come back. That'll kind of get us back in gear as well. Alright? So, but if you want in the meantime, you can practice a few of these too.